All right, as promised, we'll start on time, 9 o'clock with all, what, 6 of us? Nice, very nice. So just so you know, in the engineering world, typically 10 minutes before you're supposed to be somewhere is on time. Any later than that is late. So then, like if you're showing up at 9 for something at 9, that's late. Because there's a lot of conversation that goes on before a meeting or before whatever is scheduled. So anyway, you'll have to tune into that in a few years when you get out there. But what we're going to talk about today is the design loop and scheduling and the ping pong ball experience. So kind of all three of those, but I'd like to start with a little engineering case study. This is the Millennium Tower. Anyone familiar with the Millennium Tower? No, it's not here. It's back east. Yeah. So this is a giant tower that got built, and I'll let the news reporter set it up for you. It has some issues. This is currently ongoing. So built many years ago, but still has this existing problem. So it's just fascinating that this kind of thing still happens. Hopefully we get sound. Uh-oh, no sound. Can you see it? All right, we'll try and do something. We'll do something about that here.
The Millennium Tower is the tallest residential building in San Francisco, 58 stories above the ground and 419 luxury condominiums. The tower opened residents in 2009, but even before construction was finished, engineers could tell that the building was slowly sinking into the ground and tilting to one side. How do engineers predict how soils will behave under extreme loading conditions? And what do you do when a skyscraper's foundation doesn't perform the way it was designed? Let's find out.
We won't watch all 13 minutes, but
engineering. In today's episode, we're talking about the Millennium Tower in San Francisco. Skyscrapers are heavy. That might seem self-evident, but it can't be overstated in a story like this. An average single-story residential home is designed to apply a pressure to the subsurface of maybe 100 pounds per square foot of building footprint. That's about 5 kilopascals, the pressure at the bottom of a knee-deep pool of water. With its concrete skeleton, the Millennium Tower was designed to impose a load of 11,000 pounds per square foot, or 530 kilopascals to its foundation, about 100 times more than an average house. It would be impossible for just the ground surface to bear that much weight, especially in this case, where the ground surface is a weak layer of mud and rubble placed during the city's infancy to reclaim land from the bay. That tremendous pressure is why most tall buildings use deep foundation systems. The Millennium Tower's foundation consists of a 10-foot or 3-meter thick concrete slab supported by 950 concrete friction piles driven into the subsurface to a depth of about 80 feet, or 24 meters. Friction piles spread out the load of the building vertically, allowing much more of the underlying soils to be used to support the structure without becoming overwhelmed. The piles also allow the foundation to bear on stronger soils than those at the surface. Driving the piles so deep allow the building to not sit on the surface layer of artificial fill or even the soft underlying layer of mud, but rather on the dense sandy soil of the Colma Formation below. This is a fairly common design in San Francisco, with more than a dozen tall buildings in the downtown area utilizing a similar foundation system, including some nearly as large as this. However, it's not the dense sands causing problems for the Millennium Tower, but what's underneath. Below the Colma Formation is a thick layer of ice age mud, locally known as the Old Bay clay. Thanks to the geologists for that. When the building was designed, the project geotechnical engineers predicted that it would settle 4 to 6 inches, or 10 to 15 centimeters, over the structure's entire lifetime, mainly from this layer of Old Bay clay below the bottom of the piles. But even before construction was complete, the building had already settled more than that. I have a video that goes into greater detail about soil settlement that you can check out after this, but let me summarize the high points here. The ground below your feet may seem firm and stable, but when subjected to increased loading, and especially when that loading is extreme, like that of a concrete skyscraper, soil can compress in a process called consolidation. Essentially, the soil is like a sponge filled with water. An increased load will slowly squeeze the water out, allowing the grains to compress into the empty space. Settlement is usually a gradual process because it takes time for the water to find a path out from the soil matrix. But some things can accelerate the process, even if they're not intentional. The Millennium Tower was already designed to put more stress on the underlying Old Bay clay than any other building in the area. However, construction of the tower's basement also required the contractor to pump water out of the subsurface to keep the site dry. This is often done using vertical wells, similar to the ones used for drinking water, but usually not as deep. This deliberate and continuous dewatering of foundation soils accelerated the settlement. Then other construction projects nearby began, including the adjacent Transbay Transit Center, which required their own deep excavations and groundwater drawdowns. All these factors added up to a lot more settlement than was initially anticipated by the project's geotechnical engineers. The result was that by 2016, when the public first learned about the issue, the building had already sunk more than 16 inches or 41 centimeters, triple the movement that was anticipated for its entire lifetime. Unfortunately, that settlement wasn't happening either. Instead, the northwest corner had sunk a little lower than the rest of the foundation, causing the tower to tilt several inches in that direction. The media had a field day reporting on the Leaning Tower of San Francisco, and accusations started flying about who was to blame and whether the city had covered up details about the building's movement. The developer continued insisting that the building was safe, reiterating that all buildings settle over time, and the Millennium Tower was no different. But it definitely was different, at least in magnitude. With so much attention to the building, the city commissioned a panel of experts in 2017 to assess its safety, both for everyday use and in the event of a strong earthquake. By that time, the building had settled another inch and was out of plumb by more than a foot or 30 centimeters. That's not something you could notice by eye and was probably only discernible to the most perceptive residents, but it's well beyond the 6 inches allowed by the building code. Even so, the panel found that the building was completely safe, and the settlement had not compromised its ability to withstand strong earthquakes. However, they cautioned that the movement hadn't stopped and further tilting may affect the building's safety. At the same time, and despite engineering assessments confirming the building's safety, the condominium prices were plummeting. No one wanted to live in a building that was sinking into the ground with no sign of slowing down. It didn't take long for lawsuits to be filed. By the end of it, just about every person and organization related in any way to the Millennium Tower was involved in at least one lawsuit, including individual residents, the Homeowners Association, the building developer, the Transbay Joint Powers Authority, and many others. In total, there were 9 separate lawsuits involving around 400 individual parties. After many years of complex litigation, a comprehensive settlement of the legal kind was eventually reached through private mediation. The result was that no one took the blame for the building's excessive movement. Condo owners would be compensated for the loss of property values, and most importantly, the building would be fixed. During mediation, the retrofits to the building's foundation to slow the sinking and de-tilt the tower were a big point of contention. One early plan was to install hundreds of micropiles, small diameter drilled piles, through the existing foundation down to bedrock. But the estimated cost for the repair was as much as $500 million, more than the original cost of the entire building. Turns out it's a lot easier to drill foundation piles before the building's built than afterwards. The challenges associated with working below the building, like access, vibrations, noise, and lack of space, drove up the price, and the parties couldn't agree to pay such a substantial cost. An unconventional alternative proposed by the developer's engineer ended up resolving the dispute, and as of this writing, is currently under construction.
Amazing. Hard to believe that stuff still happens, still ongoing, still happening. Here's an article, January 26th, 22, that's about a year ago, on the fix. So existing piles here, and these are the new perimeter piles, and they're going to go around the building, around the perimeter. and go all the way down to bedrock this time. Unbelievable. What kind of engineering are we talking about here? Civil structural engineering, which are the same, right? So if you're interested in like large building construction, it is structural engineering, which starts with a civil engineering degree and then tags on a structural engineering piece. We will have a structural engineer come and talk to us this term. So he's agreed to come. Yeah. Architectural would be the design of the space, like how the big box is used, how people get up and down and move around their condos, right? But not the structural piece. The structural piece is going to be structural engineering. And there's going to be a team, right? A big team that works on that kind of project. But the buck is going to stop with design engineers that did the design work. So when they talked about that litigation, they're talking about professional structural engineers that designed the building. They're going to be involved. So when we do the whole professional engineering thing, to be or not to be, if you become a professional engineer, you are for sure responsible for anything you stamp that says this is good, it's good for the public to use it, it's safe. That responsibility is going to come back to you. There are responsibilities as just being a regular engineer too. Like if you weren't a professional engineer, but you were on this project and you did design work, which you could, right? Any engineer could do that. You don't have to be a professional engineer to do that. Your name's on documents, your name's on calculations, you will become responsible. So it doesn't eliminate your responsibility if you do not become a professional engineer. If you become an engineer, there's responsibility there. So you just got to be careful, be diligent, do your best, and usually it just works out just fine. So, and like they said, in the end, nobody was found guilty, which is hard for me to believe. Somebody's guilty. Like the tower is leaning and leaning way more than it's supposed to be. So it was what they say out of plumb 14 inches, something like that. Yeah. So that's crazy stuff. It's a very tall tower though. So like the real problem, like on the ground level, you can see the cracking as you walk around the Millennium Tower. These are strain gauges that they put on cracks to see how quickly those cracks are growing. And that'll give you live data on, in a database that could be looked at every day as far as the growth rate of this kind of thing. So, yeah.
Was the sinking taught by any calculate engineers, or is that just something that?
So, of course, everybody's doing this, right? Everyone's like, no, it was them. It was not caused by any calculation errors. It was the neighbor. So the basic gist of the design engineers were the neighboring projects were evacuating groundwater faster than the design was ever intended. So the design was intended to evacuate the groundwater, and they have the wells that do that for this building, but the building next to it is doing the same thing. And the building next to it on the other side is doing the same thing. So a lot more water is coming out of the ground than ever was anticipated, which is just settling everything. And it's not settling it evenly. Like if it went straight down, that would be different. But if it's going down like this and you have a tall tower and it starts to lean at all, that's a problem. So yeah, the residents could put an egg on the table and the egg would just take off. Like it was that sloped, and it still is that sloped. So yeah, it was just a mass evacuation out of that place. I don't know. There hasn't been any reports on the building next to it, and they're nowhere near as tall. So I'm guessing they may have settling problems, but they don't have leaning problems like this one does. So yeah, all kinds of piles being driven now. Perimeter piles is the solution. See how that works. All right, let's talk about the design loop. So we're going to talk about the design loop. We're going to talk about scheduling, and then you have a project due in a couple days to build a schedule. I'm just going to tell you now so you can think about it as I go through this. I want you to build a schedule for the ping pong ball challenge that you've already done. So if you're going to do that challenge again, How much time would you like? A lot of you said, I wish we had more time. Absolutely. The time was super compressed on that project intentionally, right? I wanted you to feel the pressure of a deadline because we feel the pressure of a deadline all the time. And you're going to feel the pressure of a deadline on the next project. Okay. So what you're going to do is build a schedule that reflects the amount of time that you wish you had. So kind of going to the I wish, almost everyone said you had more time. All right, now you get to build a schedule for that project as if you're going to do it again, right? Out however many days you want. You can do it by days or you can do it by hours, however you want. But I'll show you some examples when we get there. But I want you to then also build into your schedule the design loop, because this is how we need to attack a project. I didn't give it to you, right? Prior to that project, I want you to just be thrown into a project. I didn't give you any, like, this is how your team should function. So some teams, all teams actually function pretty well to get the project done, right? And meet the deadline. But then there was some team issues. I heard some communication issues right away, right? So there was maybe no communication system defined in your team, which is legit. I haven't gone over teamwork. So I will go over teamwork extensively one day, and we'll just talk about how that team should function as far as an engineering team goes. But we're going to focus on the design loop because this is what I want run in the next project. And I want documentation of it. So as you run the design loop in the next project, document it, take notes in your team, take notes and document each stage that you go through. I know some of you did brainstorming in the beginning of the ping pong ball project, but then you had to move, right? You had to get going. You had to pick a solution and get to it. So the design loop was run in a really micro state in the ping pong ball challenge. And I want it to be much slower and much more methodical. The solution is in the end after the loop has been run many times. Okay, so just keep that in mind. So step one is identify and define the project. So this really needs to be focused. Again, I know you didn't have time for that in the ping pong ball challenge, but you will have time for it in the next project. And this means that everybody on board the team understands the definition of the problem. Okay, so for the ping pong ball project, the definition could have been to get the ball in the bucket, right? That could have been a very simple definition. Somebody else might say, well, it's not. It's to throw the ball at the right angle, at the right velocity and force to get the ball in the bucket, right? A lot more defined than the first one. And then the next one could be, no, it's not that. It is to build a system that is adjustable and reliable to then launch a ping pong ball at the right angle and the right force to get it into the bucket, right? So we've went from toss a ball into the bucket to a much more defined problem statement. If you can get to that super defined problem statement and then all team members agree to it, then you're all trying to solve the same problem. If you don't do that, then you're all potentially solving different problems. And you don't want that in your team. You want to be everybody on board, identify the problem, like really write it out in as much detail as possible, and then move forward. So the next phase is to generate ideas, which a lot of time teams go straight to generate ideas without defining the problem, right? So then the generate ideas is just going in all different directions. So brainstorming, that is how we typically generate ideas. There are different methods to brainstorming. There is structural brainstorming, there is unstructured brainstorming, on and on and on. I have a few slides in the end about that. There's brainstorming without reality, right? There's brainstorming with reality. So like understanding the resources you have available, that can help brainstorming. If you just start randomly brainstorming, then you might not be thinking about like, how are we going to build this thing? And what resources do we have available? And how much time do we have available? All those kind of things will impact your brainstorming. So identify the problem, generate ideas, and then somehow come up with possible design solutions. Now, it's plural. Design solutions, especially in the first loop, that you could have 1, 2, 3, 5 design solutions. 5's a lot. You really want to try and narrow it down. But brainstorming should give you a long list. Like, we could do it this way, right? And we could do it this way. And in brainstorming, we're not critical of the ideas. We just let it flow, right? Write it down, let it flow, generate ideas. Then you come to best solution and you're like, okay, this one clearly we can't do because we can't build it. Or this one clearly we can't do, we don't have enough resources, money, materials, time, all of those kind of resources, right? So you start to narrow down best solution. You can come up with a system for this. It can be voting. It can be team leader decides, right? Because we'll probably have a team leader in our team. We should at least. It could be, it goes to committee and committee decides. There's a lot of different ways that solutions get chosen. It's not typically just, let's just all talk it out, right? It could be data driven, like, hey, statistically, this one's going to be more successful than this one if we had some data. So select your best solution, but what I'd like to see in the next project is how did you select this solution? Like, how'd you get there? Which again is going to be some good note taking on your meetings and how you went about things. So I'm really more curious about how you went about it than what you actually came up with, like whatever your solution is. I mean, that'll be cool too, I'm sure. But how did you get there? Like, what was the path like? What was the design loop like? What were all the pieces? That's what I'm interested in. All right, so now we've got maybe 2 or 3 solutions in this first loop. We go to testing and checking if the solution solves the problem. So a lot of time that's called prototyping. So we have this idea, we build a quick mock-up, right? Which is what you really did in the ping pong ball thing. You prototyped what you thought would work. After you launched with it, I'm sure you had like, oh, here's some other ideas. Or you looked around and saw, hey, some people are just shooting it straight with the mousetrap, like not building anything off it, and it's going pretty well, right? So that's prototyping. What you got, if you looked at everybody's, is you got like 6 prototypes to look at. And you could go, oh, that one is like doing the best, and they got one in the bucket. If I could run the design loop again, I might zoom in on a different design, right? So with the next project, hopefully you get to prototyping fairly early and you can test with it and go, oh, this is good, it's working, but it needs this tweak, or this is bad and we just need to like redesign and try it again somehow. Okay, so prototyping is big. You want to get there quick, but you don't want to skip any of these early steps either, or you're just going to loop more times, right? All right, so we prototype, and you can prototype more than one thing. You could prototype 1, 2, or 3 things. We don't do that with airplanes, right? We don't want to do that. That's too much money to be prototyping airplanes, but we do that with airplane parts. The prototype, test them, build systems to load parts, see how they react, and then redesign that. They're prototyping continuously at Leatherman on their little Leatherman tool. Like every version is going to be different and hopefully improved because they're just looping that product. And you can loop within the product, right? They might loop the little screwdriver part. So they got a team that does the screwdriver part on the Leatherman tool. And those guys are just design looping that thing to get it better and better and better. So this system can work on the big system, but it can also work on subsystems. And most often it is on subsystems, right? So think about that when you're running your design loop. You could have, portions of your team looping different parts. Well, that's very common. All right, and then we got to evaluate the solution. Communication's in the middle of the design loop and it's critical. So as some of you may experienced in your teams, communication was difficult because it wasn't defined, right? You just like said, okay, we'll all get in touch with each other, and everybody left. And that used to work back in my day because we just had the phone. That's it. But now you have so many ways to communicate. Like, hey, are we going to use Snap? Are we direct messaging in Facebook or Instagram? Are we texting each other? Are we literally phone calling each other? Are we using email? Are we using 4 emails? Like, we have unlimited amount of communication, which is a problem, actually. So in your teams, you got to decide like, hey, our form of communication is email. End of story. Everyone's got that. And then our commitment to each other is a response within how long? What do you think? What's a reasonable response time in email? 3 hours, somebody says. Anybody else got one? A working day, 8 hours, or just a full working period. Anyone else? Anyone want 5 minutes? No. Like, I'm done with the people that think I'm going to respond in 5 minutes, right? That's not going to happen. I do have in my teams, we have a primary communication system. A lot of times it's by end of day is what we do. So if an email is, and there's different priorities. If the email is important, it's by end of day. If the email is just standard, not given the important button, then that's a 24-hour cycle for our communication. But then we have a backup problem communication system. And that's actually texting. So if I get a text from one of my teammates, I know stuff's gone bad. And I need to then go to that email right away. So we only use it to alert each other that you need to go to your email and see what's going on here, right? And it works really well. But everyone's on board with that. And there's no problem until there's a problem. And then it's like, come on, this was our agreed upon communication system. You signed the document type of thing, right? So that's what you should do in your teams. It works. All right, then we're going to, I think this is evaluate the solution, right? So that's just through testing. We say, oh, this is good, this is bad. We're on the right track, we're on the wrong track. What's everyone else doing? There's nothing wrong with what's everyone else doing. That is a common theme in engineering. Like, what are they doing? Especially if they're not necessarily a competitor, but somebody who's doing the same thing. We look at each other's stuff all the time. So I guarantee if there's somebody building a tall tower in San Francisco, they're looking at the Millennial Tower to see what happened, because they do not want to repeat that. And they're sharing that information, right? So what are other people doing? That's a great thing to think about. And then it's refining. So pretty much have that loop. Now we're here. Refining means come back. Let's say, okay, ping pong ball launcher, we're actually throwing the ball too low. It's just rifling it straight, right? So now we're back here to, how do we generate some ideas to get a little more arc to that thing? So now we're here, we brainstorm that idea, we select the best thing that we want to adjust. We come here, we adjust it, we go back, we test, right? And now it's shooting at the right angle. We solve that problem. Now it's just going too far. Boom, right back to brainstorm, we can back up. So some of that happened in our little ping pong ball experience, right? But it was really unstructured because you didn't have a structure. So now you have a structure, do that with it, but please document it, because that's a big piece of what I want to see in the end of the next project, is that you ran the design loop, hopefully more than once. I know it's short of time again, even though we have the rest of the term, but hopefully we run the design loop a few times, do a lot of testing, document that. So then in the final report, I can see that process. Super important. Questions? Yeah. Yeah. But we haven't got there yet. I'm going to talk about that. Yeah. Any questions on the design loop? Does that make sense? You'll see it when you go through school. If you go off to university, you'll see the design loop in different forms. I think this is a nice little graphical form. When we get into scheduling, you'll see all different ways to schedule too. The concept of this is going to exist in any design, problem solving, engineering related system. It's going to be very similar. You identify the problem. You then generate ideas. Look at your resources available. That's so big. Even companies struggle with looking at the resources before they come up with things they want to do. And the engineering team will come up with it, but then, they go to try to get budget for it. And the folks will say, We don't even do carbon fiber, and you want to use carbon fiber, so you want us to buy all this carbon fiber equipment for this project? We're not doing it. Boom, then our loop just blew up, right? Because we didn't understand the resources available. So understand your resources, like look around, that's what you got. It's not wonderful, right? You have limited resources. But when you get out there, unfortunately, you have limited resources too. So it works very similar. All right, let's talk about planning and scheduling. Two different things. Two different things. So the gist is with planning, you want to do that before you start work, right? So planning requires an understanding of what you're going to do, the scope of the work. It's more difficult than scheduling. Scheduling is just like, hey, we know what we want to do. Now let's figure out how to get it all done time-wise, right? But planning requires that you understand like each task that you're going to do. Like if we're going to build the Millennial Tower, what is the first thing we have to do? What is the second thing we have to do? It's hard to like define all that, right? So planning is much more difficult. Each task is required to be completed in the project a lot of times before the next task. So best done with those with experience in similar projects. Break project into well-defined units of work. That's what we want to do with our task today, which is to build a schedule for the ping pong ball challenge. Now that you've been through it, you kind of know, you know, the whole thing, you've been through it. So now you get to kind of retro think it. If I was going to do it again, what's the first task I would do? What's the second task I would do? And try and define those as best you can. I've introduced the design loop to you, and I want you to use it in your schedule building for the ping pong ball challenge. Okay. And again, I'm letting you choose the time frame. If you think you need 4 months to do the ping pong ball challenge, then your schedule should show me 4 months. If you think you need 4 hours to do the ping pong ball challenge, then your schedule should show me 4 hours. But the difference is I want your project that you're going to now create. I want that ball to go in all 3 times. Right? We're not going to actually do it. But when you think about it like, oh, this is a project that we want it to work, not just come close. So how much time would that take? Right? Build that schedule. All right. Break project into well-defined units of work. It is an ongoing process, planning is, so, and your schedule's ongoing too. We call schedules a living document. It's alive. It can change. Depending on what happened yesterday, my future can change. That schedule needs to change. Happens all the time. What can't change is the end delivery. Like that can't change. The customer wants this thing at that time, they're going to get it. What has to change is my amount of time I put on the project, or the amount of people, or the amount of resources, if things change. Things don't ever change to shorten up. Things always change to get longer. I never come in the next day and go, oh, we did so good last night that we can all take tomorrow off. That doesn't happen. It's like the other way around. All right, so scheduling then requires a length of time for each task. So that wasn't planning. Planning just said, hey, we got to collect all our resources. We need the mousetrap, we need the wood, we need rubber bands, we need all these resources. We got to collect that, get it all in one spot. How long is that going to take? That's what scheduling says. It's, hey, you said you got to collect resources. How long do you need to do that? So that's what scheduling is taking all your tasks from planning, putting it into a schedule, right? Build in flexibility. That's always a good thing. Schedule includes not only durations, but sequence. Who's responsible for the task? So we'll talk about that when we do teamwork. Everybody. So when you build a schedule, you'll have tasks, things to do. Everybody should be assigned to a thing to do, and different people. So it doesn't mean that you do it. It means you're responsible that it gets done. So if you have a task that says, you know, build the arm for the mousetrap, right? And maybe it's even a little more defined than that, then maybe Troy's assigned to that task. That doesn't mean I have to do it. That means I have to make sure it gets done on time. In other words, I got to be the bird dog that is emailing you saying, you said that you were going to build this, you know, part of the arm. how's it going? Is it close? If it's not close, do you need help? I want to help because I'm responsible for this task, right? Often, if you get assigned a task, you just take it on, like, oh, I'm doing that because that's my responsibility. I make sure it gets done. That's great. You can do it that way. That's fine. But if that person needs help, they need to be honest with the team and say, I need help. It's not happening. It's not going to be done in 2 days because I am not able to do it. So that's not going to work an hour before it's due. That's going to work 2 days before it's due, right? So that requires communication saying, hey, I need help. I know I'm responsible, but I don't have a drill. I can't do it, type of thing. Okay. All right. Schedule's plan for completing work. It's not perfect. It will change and you manage it. So it's never perfect. We usually build them backwards, by the way. Customer needs this product here on the 31st. We need to have testing done on the 25th, right? Before that, we need to have design loop 4 done on the 22nd. We need design loop 3 done on the 20th. We need design loop 2 done. Maybe it doesn't take all that, right? But maybe it does. Maybe it takes more. So you work it from the end forward. So first thing you should do on your little project today is think about, okay, how much time do I want on this project? If I want it done in 4 days, then that's my time frame for my schedule, right? And I build it backwards. So as often how we do it. There was a question. No? All right. You guys are doing good. Hang in there. I could turn the light on. That's really making you sleepy. So you're going to build schedule for me today. You might want to do your planning part first, which is list out the tasks. And then you can build schedule however you want. You can build it pencil and paper on graph paper if you want. And I got graph paper if you want it. So I'm not requiring Excel by any means. Excel is simple. You're not building equations. You're just using the cells to put information. So it's really not that difficult. But if you just have never done it before, that would be a lot of extra time you maybe you don't want. Build it on paper. I don't care. It's just fine. Okay. So either on paper or in Excel, up to you. You could even use Microsoft Scheduler if you had it and you know it, but don't go to learn it. That's a big one, right? And there's a few other schedulers. But what I do want is it somehow laid out where we see tasks, clearly see them, and then we see a time frame for those tasks. And then this is called the Gantt chart, and then we fill in boxes for that time frame. So most things don't just happen and they're done. They take time. And things can overlap. You can see that there's a task here that's going to last, what, a week? Yeah, a week. And then there's another task under it that's going to start a day after this one and also last near a week. It's okay to have overlapping tasks. That's fine. If one's got to be done before the next one can start, then that's called a critical path. So some things like before you build your prototype, you're going to have a design, right? So that would mean the design is critical to the prototype, and those two typically would not overlap. Unless it's a really big project and you can build subsystems, while you're trying to come up with the overall design, that's not the mousetrap. So critical path means something's got to get done before something else. So I think this shows critical path. This task stops, this task starts, and all of these start after that task. That's a critical path. Like that's got to happen. Okay. So again, this is Microsoft Project. It does the same thing. It just is a little more, you have a lot more control over tasks. People can interact with it. People can go in and say task complete. That'll open up new tasks, that kind of thing. It loops tasks together. This would be a bigger manufacturing process than what we're going to do. But it's similar. It's got a time frame for tasks, right? Some tasks happen after other things. So it's a very similar process. These are kind of flowchart schedules. So you'll see these now and then in bigger operations. Some folks like these. I don't really like it. It's a little harder for me to follow. I haven't used them a lot. That's probably why. So Excel or some kind of graph paper. Set up your schedule. Snap a picture of it if you do by hand, upload it to Blackboard. I think I gave you until Thursday, end of day. Yeah. Nope, you can do this all on your own. Yeah, everyone's gonna do their own schedule. Like, you don't have to work with your group on this one. You just do it. This is how I would do it. This is the schedule I would build to try and pull this thing off, to try and get all 3 balls in the bucket. Yeah.
But if you like, we design our own schedule, like critical, like pathway type of thing, for example, and then we go to class on Thursday and we show our teammates hours.
You could, that'd be fun, just to kind of share like, hey, this is how long I think it would take, and this is how I would do it. So yeah, the more of these you look at, the better. You're gonna be able to see them all when they go into the submission area. So, you know, click on somebody else's. If you're just like, oh, I'm a little confused on what I should be doing, go look through them and there'll be some super clear ones, and then there'll be some sketch ones that defining the problem. It says, you know, shoot the ball in the bucket. Like, we need a little more than that.
Explain to me about that again.
Yeah, so working backwards means, well, let's just talk about the project. You have to deliver me something in 2 days, right? By end of day Thursday, you've got to submit something to Blackboard. When are you going to start working on that? Are you going to start working on that Thursday night at 11 p.m.? Well, if that's true, then you've just compressed your whole schedule into 1 hour, right? So maybe you should start working on it a little today, but in the end, it's due Thursday night, right? So maybe you think about that. That's the delivery time. Okay, if I want to do a good job, maybe I should start on Tuesday night, right? Think about all my tasks Tuesday night, and then Wednesday, think about what kind of system I want to do, pencil and paper, Excel. If I'm going to do Excel and I don't know Excel, then maybe Wednesday morning, I need to spend some time with Excel and learn that a little bit, right? Then Wednesday afternoon, I can start putting some stuff in there and start building my schedule. Thursday, I can kind of look back at what this exercise was supposed to be and make sure it's all good. And then Thursday night, I submit, right? But it all started with when it was due. Yeah. So on your next project, I'm going to put a delivery date in the calendar. And that's when your project is to be delivered to me. And then you'll have between probably this Thursday and that time to do your project. So you might think about like, oh, I got to deliver it here and test it. We want good testing, 2 weeks before that. We want design loop before that. You just build it backwards from the delivery time. That makes sense? Kind of? Okay. Questions? Yeah, that's good enough. I was going to go into brainstorming, but I think I'll wait on that. There's 2 types, structured and unstructured. I'll put the slides up, you can look at it. But brainstorming can be kind of awkward because it seems like the most chatty folks get the most brainstorming out, and the quieter folks just sit and think. I'm typically a very quiet person during brainstorming because I like to think about stuff. I have gotten better at when somebody asks me a question, I immediately respond and say, I'm thinking about that. Because they don't know what I'm doing. Like, you ask me a question, I'm sitting there going, and they're like, did you hear me? I'm like, yeah. Oh yeah, I heard you, right? But I'm thinking about it. So my wife's gotten used to that. She'll ask me a question and I'll go, I'm thinking about that. So then she'll wait. Like, oh God, he's got to think about the shit, right? But in the beginning, I just didn't say anything to her. She'd be like, hello, did you hear me? I'm like, yeah, I'm thinking about that. So it's good. If you're a thinker, tell them you're thinking about it. Like, give me a second, I'm thinking about that. So brainstorming can be like blah, 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 people just spitting stuff out and other folks are quiet. So I like the structured brainstorming, which means everybody speaks in turn. It works good. And if you don't have anything to say, you say pass. Feels weird, but it works really good. Like, it shuts people up, which is good sometimes, but it also keeps a flow of information, right? All right, that's good. We're good. Thanks for coming. Geez, without you guys, we'd have nobody. We're down to about half the class coming to lecture, so that's disappointing, but it's life. Maybe they're getting it in the recording, right?